Welcome to the first chapter of our exploration into the quantum internet. Today, we're diving into a groundbreaking concept that could redefine how we communicate and share information. So, what exactly is the quantum internet? To understand this, we first need to grasp the basics of quantum computing and networking. Quantum mechanics is a branch of physics that describes the bizarre behavior of particles at the smallest scales. Think atoms and subatomic particles. Unlike the classical bits used in today's internet, which can be either a 0 or a 1, quantum bits, or qubits, can exist in multiple states at once, thanks to a phenomenon called superposition. This unique property allows quantum computers to process information in ways that classical computers cannot. Now, let's connect this back to the internet. The traditional internet relies on a network of servers and routers that transmit data using classical signals. However, the quantum internet leverages the principles of quantum mechanics to create a new kind of network that promises to be faster and far more secure. Imagine a communication system where data is transmitted not just as zeros and ones, but as entangled qubits that can share information instantaneously over vast distances. This is the essence of the quantum internet, a revolutionary advancement that not only enhances the speed of data transfer, but also introduces unparalleled security features that could make hacking nearly impossible. In this chapter, we'll set the stage for understanding the science behind quantum communication, its potential advantages, and what this could mean for the future of technology. So, let's dive deeper into the fascinating world of quantum mechanics and uncover the foundational principles that make the quantum internet possible. Now that we have a foundational understanding of what the quantum internet is, let's delve into the science that makes it possible. At the heart of quantum communication are two key concepts: quantum entanglement and quantum key distribution, or QKD. First, let's talk about quantum entanglement. This phenomenon occurs when two or more particles become linked, meaning the state of one particle is directly related to the state of another, no matter how far apart they are. Imagine you have a pair of entangled qubits. If you measure one and find it to be in a particular state, the other qubit will instantly adopt a corresponding state. This instantaneous connection seems to defy the limits of classical physics, where information cannot travel faster than the speed of light. This property of entanglement is crucial for quantum communication. It allows for the creation of secure communication channels, where any attempt at eavesdropping can be detected. If an unauthorized party tries to intercept the entangled qubits, the very act of measurement alters their state, alerting the communicators to the breach. Now, let's move on to quantum key distribution, or QKD. This is a method used to securely share encryption keys over a quantum channel. The most well-known protocol is BB84, developed by Charles Bennett and Gilles Brassard in 1984. In QKD, qubits are transmitted between two parties, let's call them Alice and Bob, using polarized light. They each randomly choose measurement bases and share their results. If they find discrepancies, they know someone may have intercepted their communication. The beauty of QKD is that it relies on the fundamental laws of quantum mechanics to ensure security. While classical encryption can be broken with enough computational power, the principles of quantum mechanics provide a level of security that's theoretically unbreakable. Understanding these concepts, quantum entanglement and QKD, sets the stage for appreciating how the quantum internet will revolutionize communication. In the next chapter, we'll explore the advantages of quantum internet over our current systems, particularly focusing on security and speed. So, let's continue our journey into the future of communication. Now that we've explored the science behind quantum communication, let's discuss the compelling advantages of the quantum internet and why it has the potential to revolutionize how we connect. First and foremost is unbreakable security. One of the most significant benefits of quantum internet is its ability to provide enhanced security through quantum key distribution. Unlike classical encryption methods, which can be vulnerable to hacking, the security of QKD relies on the laws of quantum physics. If an eavesdropper attempts to intercept the qubits being exchanged, it would disturb the system, making their presence detectable. This means that users can be confident in the integrity of their communications, drastically reducing the risks of cyber attacks and data breaches. Next, we have speed and efficiency. Quantum internet has the potential to dramatically increase data transmission speeds. Thanks to the phenomenon of superposition, qubits can carry more information than classical bits. This means that vast amounts of data can be transmitted simultaneously, leading to faster download and upload speeds. For applications that require real-time data processing, such as online gaming, streaming, or even autonomous vehicles, this could be a game changer. Additionally, the quantum internet could revolutionize data-heavy applications. Industries like artificial intelligence and big data analytics thrive on processing massive datasets quickly. The ability to transfer and process this data faster and more securely could lead to breakthroughs in various fields, including healthcare, finance, and environmental science. Moreover, quantum networks could enable new forms of communication, such as quantum teleportation. This method allows for the transfer of quantum states between distant locations without physically sending the particles. While still in experimental stages, this could lead to new ways of sharing information securely and instantaneously across the globe. Finally, let's consider the potential for distributed quantum computing. By connecting quantum computers over a quantum internet, we could create a network of quantum systems that work together to solve complex problems. This could vastly enhance computational power and lead to advancements in research and technology that we can hardly imagine today. In summary, the advantages of quantum internet, unbreakable security, increased speed, and the potential for new applications position it as a transformative force in the digital age. In the next chapter, we'll take a closer look at the current state of quantum internet development and the key players leading the charge in this exciting field. Let's continue our exploration. As we dive into this chapter, let's take a closer look at the current state of quantum internet development. This is a rapidly evolving field, with many exciting advancements and key players working to bring quantum technology to life. To start, we have several leading companies and research institutions that are at the forefront of this innovation. IBM has been a major player in quantum computing and has been actively exploring quantum networking. Their Quantum Network initiative aims to connect quantum computers across different locations, enabling secure data sharing and distributed computing capabilities. Google is another significant contender, having made headlines with its achievement of quantum supremacy. Their research focuses not only on quantum computing, but also on developing quantum communication technologies. Google's advancements in this area could pave the way for robust quantum internet infrastructure. Additionally, NASA and various national laboratories, including the Los Alamos National Laboratory and NIST, National Institute of Standards and Technology, are conducting groundbreaking research in quantum communication. These institutions are exploring quantum entanglement and developing experimental quantum networks to test real-world applications. In recent years, we've seen remarkable breakthroughs and milestones in quantum internet development. For instance, the first quantum satellite, Micius, launched by China in 2016, successfully demonstrated quantum key distribution over long distances. This satellite has established secure communication links between ground stations, separated by hundreds of kilometers, showcasing the feasibility of space-based quantum communication. Moreover, researchers have developed quantum repeaters, which are essential for extending the range of quantum communication. These devices can amplify and transmit entangled qubits over long distances without losing their quantum properties, addressing one of the key challenges in building a practical quantum internet. Several countries are investing heavily in quantum technology research. The European Union, for instance, has launched the Quantum Internet Alliance, aiming to establish a pan-European quantum internet by 2030. This initiative brings together academia, industry, and government to create a network that will enhance security and data integrity across the continent. Despite these advancements, it's important to note that the quantum internet is still in its infancy. Many technical hurdles remain, such as scalability, infrastructure development, and maintaining the stability of quantum states over longer distances. However, the progress we've seen so far is promising and suggests that we are moving closer to a functional quantum internet. As we look to the future, it's clear that the journey toward a quantum internet is well underway, with significant investment and research driving this innovation. In the next chapter, we'll explore the potential applications of quantum internet technology and how it can impact various sectors, from cybersecurity to healthcare. Let's continue our journey into the future of communication. In this chapter, we'll explore the incredible potential of the quantum internet across various sectors. From cybersecurity to healthcare, the quantum internet could transform industries in ways we're only beginning to imagine. But, as with any emerging technology, there are both promising opportunities and notable challenges. One of the most talked about applications of quantum internet is in the field of cybersecurity. Traditional encryption methods rely on complex algorithms that can potentially be cracked by sufficiently powerful classical or quantum computers. In contrast, quantum key distribution, QKD, offers a new level of security based on the principles of quantum mechanics, making eavesdropping virtually impossible. Unhackable communication. As we discussed in earlier chapters, the security in quantum communication is inherently stronger because any attempt to intercept the data changes its quantum state, alerting the sender and receiver. Ideal for sensitive data. Industries like banking, government, and defense could see significant benefits from quantum secure networks, where the protection of confidential information is critical. Konzentrationsgrad of high cost and complexity. Building and maintaining a quantum secure network is incredibly expensive. Current QKD systems are limited to short distances, and developing the necessary infrastructure will take years. Compatibility with existing systems. Integrating quantum communication with classical networks poses a challenge. Until this issue is resolved, we may not see widespread adoption of quantum-based security systems. Quantum internet could revolutionize how healthcare providers share sensitive medical data. From patient records to real-time consultations, secure communication is paramount. A quantum-secured healthcare system could allow hospitals, research institutions, and doctors to exchange data without fear of breaches. Protection of patient data. Quantum-secure networks could ensure that patient information remains confidential and safe from cybercriminals. Improved. Research collaboration. Secure quantum communication could foster more international collaboration on medical research by enabling scientists to share data without risking intellectual property theft. High implementation costs. The healthcare industry would need to invest heavily in new infrastructure to adopt quantum communication. Many healthcare providers, especially in smaller institutions, may find it difficult to justify these costs initially. Technological integration. Hospitals would need to overhaul existing digital systems to work with quantum-secured networks, which could lead to operational challenges during the transition. The quantum internet's speed and capacity could have a profound impact on artificial intelligence, AI, and big data analytics. These fields rely on enormous datasets that need to be processed and transferred quickly. Faster data transfer and processing. Quantum communication could enable AI systems to process and share massive amounts of data in real time, leading to quicker decision-making and more advanced AI algorithms. Improved AI collaboration. With quantum internet, AI systems in different parts of the world could work together more efficiently, sharing data and improving outcomes in fields such as autonomous vehicles and robotics. data handling, and storage issues. The infrastructure needed to manage quantum data streams is still under development. While quantum internet would allow faster transfer, we may face bottlenecks in how this data is stored and retrieved. Limited availability. The advanced technology required for quantum communication may not be accessible to all organizations, particularly smaller ones, which could create inequality in the AI and data sectors. Quantum internet could pave the way for instant global communication. Current internet protocols experience delays, especially over long distances. Quantum entanglement could eliminate this latency, enabling real-time interactions between individuals or devices, regardless of geographic location. Instant communication. For industries that rely on real-time data, such as stock markets or autonomous systems, quantum internet could provide a significant boost in performance. New communication protocols. Quantum teleportation could create entirely new forms of communication, where information is transmitted instantly over vast distances without physically sending signals. Technological hurdles. Quantum communication over large distances remains a challenge. Technologies like quantum repeaters are still in development, and full-scale global quantum communication may be decades away. Infrastructure development. Upgrading existing communication networks to work with quantum technology will be expensive and time-consuming. Lastly, the quantum internet could allow distributed quantum computing, where multiple quantum computers are connected in a network to solve complex problems collaboratively. This could unlock previously unattainable computational power for tasks like drug discovery, climate modeling, and cryptography. Unprecedented computing power. By linking quantum computers across the world, we could dramatically increase our ability to solve complex problems faster than ever before. Collaborative problem solving. Scientists could work on global challenges in real time, with quantum computers sharing resources and processing power through the quantum internet. High operational costs. Quantum computers are already expensive to build and maintain, and linking them into a global network would multiply these costs. Limited accessibility. Like many advanced technologies, quantum computing and quantum internet may initially only be available to wealthy corporations and governments, potentially widening the technology gap. In summary, the potential applications of quantum internet are vast and could reshape industries ranging from cybersecurity and healthcare to AI and telecommunications. However, along with its many advantages, there are significant challenges and costs that need to be addressed before these technologies become widely accessible. In the next chapter, we'll discuss some of these technical hurdles and the path forward to making the quantum internet a reality. Stay tuned. As promising as the quantum internet is, it's essential to recognize the significant challenges and limitations that lie ahead. In this chapter, we'll explore some of the key hurdles that need to be overcome to realize the full potential of quantum communication. First, let's delve into the technical hurdles. One of the most pressing challenges is the technical complexity involved in creating a robust quantum internet. Scalability. While we've seen exciting developments in small-scale quantum networks, scaling these systems for widespread use is a daunting task. Current quantum communication technologies are typically limited to short distances. Quantum repeaters are still in the experimental stage, and significant advancements are needed to extend the range of quantum signals without losing their properties. Quantum state stability. Qubits are notoriously fragile. They can easily lose their quantum state due to environmental noise, which can lead to errors in data transmission. Maintaining the stability of qubits over longer distances is critical, and researchers are working on various error correction techniques to address this issue. Next, we face the challenge of infrastructure development. Building the infrastructure required for a quantum internet will be a massive undertaking. Cost. The development and deployment of quantum communication systems come with high costs. From specialized hardware to new transmission lines, the initial investment required can be a significant barrier, especially for smaller companies or developing nations. Integration with existing systems. Transitioning from classical to quantum networks presents challenges. Current internet infrastructure is not designed to support quantum communication, and integrating these two systems will require careful planning and significant resources. Economic and regulatory barriers also pose significant challenges. Investment requirements. Governments and private sectors must invest heavily in research and development to make quantum technology viable. Securing funding and resources can be challenging, especially when the benefits of quantum internet may take years to materialize. Regulatory frameworks. As with any emerging technology, developing regulatory frameworks that address privacy, security, and ethical considerations is essential. Policymakers need to create guidelines that foster innovation while protecting users and ensuring fair access to quantum technologies. Limited accessibility is another concern. Currently, access to quantum technologies is highly concentrated among a few key players, large tech companies, and government labs. This raises concerns about inequality in access to future quantum resources. Knowledge gap. There is a limited pool of experts in quantum technologies, and training a workforce capable of operating and maintaining quantum systems will take time. Educational institutions will need to step up to meet this demand. Global disparities. If quantum internet becomes a reality, there is a risk that only wealthier countries or corporations will have access to these technologies. This could exacerbate existing inequalities in technology access, leaving developing nations at a disadvantage. Lastly, public perception and awareness are crucial. Public understanding of quantum technologies remains low. Complexity of concepts. Quantum mechanics is inherently complex, and the concepts surrounding quantum communication can be challenging to communicate effectively. Misinformation or misunderstanding can lead to skepticism about the technology's safety and applicability. Building trust. For quantum internet to gain widespread acceptance, users need to trust its security and reliability. Building this trust will require transparent communication about how quantum technologies work and their benefits and risks. In summary, while the potential of the quantum internet is enormous, numerous challenges and limitations must be addressed to make it a reality. From technical and infrastructural hurdles to economic and accessibility issues, the path forward is complex. In the next chapter, we'll look at the future of quantum internet, exploring predictions for its mainstream adoption and the potential impact it could have on society and global communication. Let's continue our journey into the future of technology. As we explore the future of the quantum internet, it's essential to consider both the potential timeline for mainstream adoption and the profound impact it could have on society and global communication. In this chapter, we'll delve into expert predictions, ongoing research, and the transformative possibilities of quantum technology. Predictions for mainstream adoption. Many experts believe that we are on the brink of a quantum revolution, but the timeline for widespread adoption varies. Short term, 1 to 5 years. In the near term, we can expect to see advancements in quantum key distribution and small-scale quantum networks being deployed for specific applications, especially in sectors like finance and government. Companies will likely use quantum technology for enhancing security measures, creating pilot projects that demonstrate the capabilities of quantum communication. Medium term, 5 to 10 years. As research progresses, we may begin to see the establishment of more extensive quantum networks, particularly in urban areas. Initiatives like the European Quantum Internet Alliance aim to connect various cities with quantum communication capabilities, laying the groundwork for a more robust infrastructure. Long-term, 10-20 years. Looking further ahead, the vision of a fully operational quantum internet may become a reality. Researchers predict that by the late 2030s, we could have a global quantum internet that connects quantum devices and facilitates secure, instantaneous communication across vast distances. This would open new frontiers in everything from telecommunications to scientific collaboration. Impact on society and global communication. The implications of a quantum internet extend far beyond technology. They could reshape how we communicate, collaborate, and even think about privacy. Enhanced global collaboration. A secure and rapid quantum internet could foster unprecedented international collaboration on research and innovation. Scientists across the globe would be able to share data and findings in real time, leading to faster discoveries in fields like climate science, medicine, and technology. Transforming communication norms. The way we communicate could change dramatically. With the potential for instant and secure messaging, new platforms could emerge, prioritizing privacy and security. This may lead to a cultural shift in how we perceive communication, with greater emphasis on confidentiality. New business models. As quantum internet technology matures, it could give rise to entirely new business models. Companies may develop services that leverage quantum communication for secure transactions, enhanced data analytics, or innovative AI applications, creating a ripple effect across industries. Shifting power dynamics. The introduction of quantum internet could also alter power dynamics on a global scale. Nations that lead in quantum technology development may gain significant advantages in cybersecurity and data integrity, influencing international relations and economic power structures. Ethical considerations. As with any transformative technology, the quantum internet will bring ethical considerations to the forefront. Privacy versus security. The balance between enhancing security and protecting individual privacy will be a critical issue. While quantum communication offers unprecedented security, it also raises questions about surveillance and data ownership. Access and inequality. Ensuring equitable access to quantum internet technologies will be crucial. Policymakers and industry leaders will need to work together to create frameworks that prevent a technology gap between wealthy and developing regions. Public engagement. Engaging the public in discussions about the implications of quantum technology is essential. As quantum internet becomes more prevalent, fostering understanding and trust will help mitigate fears and misconceptions. In conclusion, the future of the quantum internet is both exciting and complex. While we're still in the early stages, the potential for transformative changes in communication, security, and collaboration is immense. As we continue to navigate the challenges and opportunities ahead, one thing is clear: the quantum internet could redefine the way we connect, share, and innovate in the years to come. In our final chapter, we'll wrap up our exploration and summarize the key takeaways about the quantum internet and its significance in the digital age. Let's conclude our journey. As we reach the end of our exploration into the quantum internet, it's time to recap the key points we've covered and reflect on the significance of this groundbreaking technology. We began by understanding what the quantum internet is and how it leverages the principles of quantum mechanics to revolutionize communication. We explored the science behind quantum communication, focusing on critical concepts like quantum entanglement and quantum key distribution, which provide enhanced security that is virtually unbreakable. We then discussed the advantages of the quantum internet, including its potential for faster data transmission and unprecedented security. We examined the current state of development, highlighting key players and recent breakthroughs, such as the successful implementation of quantum key distribution and the role of quantum satellites. However, we also addressed the significant challenges and limitations that need to be overcome. Technical hurdles, infrastructure development, economic barriers, and public understanding will all play crucial roles in determining the timeline for widespread adoption. Next, we delved into the vast potential applications of the quantum internet across various sectors, including cybersecurity, healthcare, artificial intelligence, telecommunications, and distributed quantum computing. Each of these areas could experience transformative changes as quantum technology matures. Looking ahead, we discussed predictions for the future of the quantum internet. Experts foresee a gradual progression from small-scale applications to a fully operational global quantum network within the next couple of decades. The implications for society could be profound, reshaping how we communicate, collaborate, and approach privacy and security. As we conclude, I encourage you to stay informed about the developments in quantum technology. The field is rapidly evolving, and the quantum internet is just one part of a larger technological revolution that promises to change our world in ways we can only begin to imagine. Whether you're a technology enthusiast, a professional in the field, or simply curious about the future, engaging with this topic is essential. Share this knowledge, discuss it with others, and consider how these advancements could impact your life and the world around you. Thank you for joining me on this journey into the fascinating world of the quantum internet. If you found this video insightful, please like, subscribe, and share your thoughts in the comments below. Let's keep the conversation going as we navigate the exciting future of technology together.